can record on a computer, and then I will share it later. Put in the drive somewhere. Okay.
I often see you have recordings of your thoughts, like just your records, right?
No, actually, the problem is that this Zoom link is generated by my account. If it was the program Zoom link, it could be recorded automatically in their code. Am I right?
Right.
This is my account. So if we use the program Zoom link that's generated before, and I ask you to share, it could be recorded on the cloud, the Fields cloud.
Well, yeah, because this Zoom link is created at
Yeah,
your
yeah,
account, so
that's
even
my.
if we report to the cloud, it's gonna be the cloud of your account.
Okay, fine. Okay. So I will share it later with everyone. Okay, fine. So thank you, everybody. That's a pleasure to be here, and I'm happy to share an idea. This is an idea as well, because since the beginning of this program, I talked to you about this idea, and we share it, we discussed, and today I want to share with you and get feedbacks to progress. Actually, the topic is robust H infinity control. It will be compared with nominal LQR control. So when we have a system, any mathematical system that there is some inputs and output, we can make a system and make a control, and that will be a closed loop control system. In that case, we can have different type of controls, like PID or K full control or neural network control, and then we will make a loop. So we have a mathematical model that represents the reality, and we have the inputs, and we have a reference system, then the output, and we can control for any deviation of the output from the reference system, and then make the feedback to the system and control for those deviations. So it means that meanwhile, we need some sensors to measure and then make the control. So, but you know that all systems face the uncertainties, different type of uncertainties that we will discuss. So a proposal or an alternative to regular control is H infinity control or robust control that are called H infinity, and I will talk about this. The talk has some slides that are more or less technical. I don't know if you are interested to talk about those technical, or I can jump. Please give me feedback if you are not interested to focus on those parts, okay? So what happened? Generally, we have a state space system, which is LTI system here, because the parameters are time independent. So, and here we have two inputs to the system, omega and u. Both are inputs. The u is the input to the system that is in your control. This is the control that the modeler can use, and the omega stands for external, or the disturbances that can happen in the system phase, and X is the state. It could be of any dimension. So this is the closed loop transfer that usually used to set up the control. And for uncertainty, we also can have additive control. So it could be H infinity, or I will discuss later what do I mean by this. But generally, if we don't have omega and it is a regular one, okay, so we use generally the Laplace transformation for the control. Okay, so yeah. This is the additive, to incorporate the omega as well. Yep. So in LQR control, which is linear quadratic regular controller, as you see, we have different measures. The classic or the standard measures or margins are the gain margin and also the phase margin. Actually, the gain margin and phase margin are used to measure how the system will respond to any input. Okay, so as you know that the phase shows the angle of the system, and the gain margin shows the magnitude of the response. Also, these are single, but to combine them, usually the disk margin is used. That is a combination of both of them, the magnitude and the angles. So in the disk, you can see where the system is stable and where the system is not stable. So within the disk, the system will be stable, and out of that, the disk, the system will be unstable. So, however, there are some limitations for this LQR system because they do not consider the robustness in industrial applications like the neuroscience that you are working. So from the beginning of the topics about this robust control, there have been more critiques against the LQR and to develop some, actually tools to control for the uncertainties that we have. So actually, the main goal of the control is to stabilize the system. So as I mentioned, when you have a mathematical system, an input and output, and you have a reference system, there will be a perturbation and the deviation from the reference system. So to stabilize the system, you can use the control like PID or the full control. Okay, so but there are some challenges. The first is that in reality, the system are different from what we model. The model is so simplified. So, and this simplicity may ignore some part that are important in the reality. So this is the main concern. There are also stability, uncertainty in the parameters, okay? So then in that case, if we have uncertain parameters, so we will lose the robustness. And also maybe there are some external disturbances in system. This was that I incorporated in the first mathematical model at the beginning, in addition to the other U input, okay? So, and also maybe there are some challenges regarding the sensors that you measure, and these are also can make some challenges. And generally, the LQR are used in single input, single output models, but in multi-input, multi-output control models, we need more robust measures. So we need the robust control. Okay, so these challenges requires that we think about a robust control. Okay, so as I mentioned, not only the environmental uncertainties are important, but also the worst case control is important. In a work that I was, in a paper that I was working, the concern was that in terms of the pandemic, we have the containment policies. So the goal of containment policy is to control the outbreak. So the government set this set of policies as the input to the system, okay? So, but the uncertainty about the behavior of the individual in response to those policies, so was my concern, how can affect the results. So then I considered the response of the individual to the containment policy as an external shock to the system. So that disturbance was modeled and we controlled for those. So any of these cases that I call, and in the literature is called worst cases, that is extreme cases that can happen. So to control for worst case, we use the robust control. Okay, so
Why are they extreme cases? It's an interaction. Is it you saying like the public respond to the policy in an unexpected way,
mhm.
but is there a reason for classifying that as an extreme strong perturbation versus just a small effect?
In that case, I assume that is extreme case because the regular control assumes that the government has some measures to control the system. Okay, so the government can set the fine-tune the policies to control the outbreak. Okay, so but there are some uncertainties. The one of the key uncertainty was the response of the individuals that comes from the environment. So you can consider other type of the, for example, economic uncertainties, any other shocks. So these are considered generally as extreme cases that can happen, and we need to control for them. Okay, so to stabilize the system when these uncertainties could happen. Okay.
Okay, that's like a judgment rather than some procedure to decide whether that's a strong or a weak.
Mhm. The worst here, you mean why do we call it the worst case? Yeah, because it is
Or a shock. Like, how do you know it's a shock versus a small?
you mean that, oh yeah, you are talking about the magnitude impact of the shock.
Yes.
Okay, so it's important. No, there are 2 points. One point is that what you consider these shocks, these are environmental shocks that are out of the system that can affect the system. Okay, so, and the other point is that why we are talking about worst case and H infinity norm. So because, you know, I will talk when I explain mathematically what H infinity means. You know, we have 2 type of the controls, H2 and H infinity control. H2 control stands for the regular controls that we have, but we have also the maximum, the maximum impact that are come from the external shocks that can be, for example, like that I explained in my model, or maybe the body movement in the other neurotherapies or neuro treatments. Okay, so this external means the maximum level of impact in your term that you consider. Yeah, but generally they come from the environment. Okay, so this means that there are disturbances that are not modeled directly in the system. Okay, so, and here we need the worst cases. The worst case, as I explained, is the peak gain for a given uncertainty range. For example, we have uncertainty regarding the movement of the body during the treatment that you have. For example, the Parkinson therapy that you have, the DPS. Yeah, the movements that. So, and actually, in robust control design, the system performance is measured in terms of the peak gain. Okay, so the H infinity norm is for this to measure this peak gain, and I will show how is it. So, and as I explained, the H2 and H infinity norms in robust control, the H2 norm measures average energy in the system, and the H infinity controls for the worst case energy into the system. And based on this energies that comes from the external disturbances, we can set a feedback, okay, to minimize those energy into the system. Yes.
So how are the norms defined? Because basically similar to norms, but
Yeah, I will explain it. So, And for the applications, we can use these norms for the performance analysis control designs. So, and however, we have the edge optimal control approach is important in this talk that I want to focus more. So if we have specified a model, okay, and with the additive perturbation and output disturbances that have, so we can have perform the constraint optimization, and then our objective is to seek for the controller that are feasible for the robust stability, okay, and also to incorporate the cost of this controller as well. So here is the definition of the H infinity. This is the basic definition that if you have, for example, this is a transform function. So, and this, in this case, this is supremum, okay, of the sigma. So it is those peaks that you can consider. For example, if you have a transfer like this, so this is the maximum, or the least maximum that can happen, the peak that you can compute. So this is the definition. So, and if this norm is less than 1, then guarantee that the system is robust. Otherwise, it will be amplified and it will be unstable. And
Sigma is what, the power spectrum?
sorry?
Sigma is power spectrum? Or what does sigma mean?
Sigma is this is the norm that this is the sigma could be the norm at each stage, you know, that the least maximum, that supremum definition, by the definition is this is the norm, is the square root of this is a square root of the trace of the system. Should I explain? Yeah, the square root, the sigma, yeah, you mean that's the square root of the trace of the system that you have.
It's basically like max.
Yeah.
What is like T?
Supremum,
Max.
the least maximum, yeah, that point is the supremum.
What is the function?
T is a transform function that you have. You know, you have a system, okay, you can have the transfer function, Laplace transfer, and based on that, you compute the measure, okay? So then this is the supremum of the measures.
Everyone, you could say for myself, I learned a little bit of systems theory, but I'm not sure everyone remembers, you know, all the basic terms like transfer function, stuff like that.
Yeah.
Maybe it's good to say a little bit about, you know, just to give some intuition, what are the transfer function represent?
Is that like a good toy example to sort of?
No, it's not. And actually, we had a system. We started this system in control. We used the Laplace transfer. Yeah, that is to measure the.
Minimize.
Yeah, exactly. You know, actually, when you have a system, okay, like that, let me start from the scratch. You know the terms. You have a system, for example, then you measure you measure the performance of the system. Okay, the performance of the system is the norm of the system. Okay, so and also the disturbances also they pulse the energy into the system. Okay, and you can measure that. You know what does it measure? Okay, so and this actually compares that the system performance with respect to the energy comes from the external or the worst case disturbances.
So essentially, it's a minimization of disturbance.
Yeah, actually, the system goal is to minimize the disturbances, so it's to establish the system, but to establish it, consider the maximum disturbances comes from, or energy from the external shocks to the system.
The transfer function is intuitively measure of the increase in energy.
Input to input to output.
You want to minimize
here I explained that this is the transfer function. If you consider, for example, if you have just, suppose that you have just one input ut, okay? So then usually the transfer function will be this part, okay? So, but in case that we have the external shocks as well, I incorporated just to represent, yeah, that's a simple model.
Is there like a standard, like simple physical example?
Yeah, that's just to represent what does it mean, the norms, the H and H infinity control, yeah.
Would you
Yeah.
say like, I mean, what's like the standard physical example?
Oh, you are looking for that, you just, yeah, just give me a sec. I had,
You tell me.
yeah,
Tell
yeah.
What's the spherical count for transfer?
Oh, may I, yeah,
For-
here is the simple example. Just let me share this one. Here in this example, I try to represent a system that is actually, this is the LTI system is a state system that we have, and the matrices shows that the coefficients that you have in system. So the deriving is A, which shows the state of the system, and U is the input. So the matrix B is the coefficients that you can represent this. So, and based on this, I computed the actually the result. This is the transform function that I had. So, and this is the transform function that I was talking about. And based on this, in this simple example, this G is the norm in L2, okay, because the model is 2-dimension, okay? And so we can compute this, the integration of the trace of this system G prime. Sorry, that's a star. I'm sorry, it should be prime. So, and then we can use the Lyapunov-based formulation to compute that one. And so generally the G is the trace of the P that you asked about. What is the P here? So, and
Can you just explain the bit there? Like, what do you?
this is formulation to compute actually the norm. So the P is contributivity gradient. So the gradient is computed from this algebraic function, is algebraic form, and you have A and A transpose, and you compute the P, and you have the C, and you can compute this norm based on this trace of this matrix.
I think what John was asking was if there's a like physical example you could give, like maybe a pendulum or
I have nothing in my basket right now, but yeah, just I wanted to show some simple, this is the computation. For example, I computed here the norm that is, for example, it's less than 1, and the system will be stable. At least we can conclude that this computation shows that this system is stable.
Can we just like agree on a simple, metaphor or whatever? It doesn't need to be like worked out numerically, but
maybe I can about that. The transfer function is a relationship from the output.
Yeah.
So you think about like a discrete time. If the gain, the transfer function smaller one, so that's kind of like always like go down. Yeah, that's like a stable. But there's like the frequency domain, right? So that means at any frequency, those gains should be smaller one. Then that's kind of like H infinity. Okay. So relationship always like smaller. So that they can go down. Yes.
So it's kind of the worst case, right?
And also let me. And
people can also do it after the pendulum. Yeah, when you have like something move and you want to stabilize it, so what are the forces you need to?
okay.
to put on ambiguity to stabilize, right?
Yeah, that was for H2, and here I computed the H infinity. So this is a system again. So, and it's a MIMO system 2x2 to input to output. So actually, again, we compute, and then here is the supremum of the sigma that we were talking. So, and here the interpretation is that in the case of the worst case, and L2 in fact shows the gain that we have from the input to the output. Yeah, that was the gain from the impact of the input to the output that we have. So system is defined in 2 dimensions here. Yeah. And this is bounded real lemma. I don't want to talk about this lemma. And here is the G infinity. This also is 4% that you know about the normal system. Okay. So, and when we have the omega is equal to, and for omega peak is 0, if we assume so, because we assume that D is 0, so then this will be 4% above the normal. The gain will be 4% above the normal gain.
So this system is unstable for very.
Yeah, it's stable. So both these 2 norms shows that the system is stable, because the H2 was less than 1, so the system shows that it's stable. And here the H infinity in the case of the peak was just 4% above the normal. That means that it's stable because the magnitude is less than 1, again, the maximum here.
Is it not stable or unstable?
Is it stable? So, no, it's stable too. No. It's stable because it's compared with the norm, which.
And what's the norm?
The norm. Just let me show here. Just let me go to this one. I will. Yeah, here I think that this figures will solve some. Maybe I couldn't explain. You know, actually, the nominal is when there is no disturbance in the external disturbance or environmental, so the system will be here. And you know, if you have, you know, the uncertainties, when the uncertainties increases, okay, so this performance shows that the system performs degrade, okay, it will be worsened, okay. So this is the maximum tolerance that the system can tolerate, okay, the maximum level of disturbance that the system can tolerate. Above that, the system will be totally unstable. Below that could be stable. This is the red line, is the maximum tolerate for the system. So above that point, the system will be unstable, okay? So here we can also set, but the modeler can set, for example, in this figure, just let me show here. Here the modeler set the maximum tolerance for this point, 1.8. So below that, the system is considered stable. So the gain is from the here to here. I think that I have the figure for that. Yeah, this is the figure that we were, for example, this is point that we said the worst case, okay, and this is the worst case gain when we have the control the system using the robust control.
How do you calculate the worst case threshold?
Here, this example.
General.
I showed that in the worst case that we use the transformation and H infinity.
That's it. What's the
Yeah,
H?
yeah. Here is in H infinity, I computed here. This is the procedure to compute, okay? And this is H infinity that is, for the worst case, the H infinity is 1.04.
Yeah, but this is below the norm, right?
This is the point that if you set that H infinity be less than a threshold, okay, you wanted to stabilize the system and you set that, okay, so it should be, if it is below that threshold, it is stable, otherwise it's unstable. For you, when you set the, yeah, this is a good question.
you.
Yeah,
there,
yeah,
threshold.
yeah.
You have to work.
Yeah, to me, yeah, that's, yeah,
So
the
you could do
threshold.
like interval of like safety.
Yeah, the safety, yeah, the safety needs for the system. Yeah, you can, yeah, exactly. You can set the interval for the safetiness, and then you can say, okay, this is the threshold, the minimum threshold, maximum threshold, this interval. So below that, the threshold, the system is stable. Because, you know, we cannot totally develop a model to follow the system 100%. So this is the control. We wanted to stabilize the system. So we set the threshold and say, okay, the maximum threshold is this, and we can tolerate up to this point. In the banking system, also, they use this stress testing, okay, in the case that there are financial disturbances. Okay. So where are we here? So, and here, as I explained,
Can I ask a big picture question?
Yeah.
Like, so what you're talking about here is a extension of sort of standard robust control in this formulation of like worst case. Is that what's your sort of main point that you're kind of focusing on here? That's like the new bit. You're saying this is the standard approach is like that original control equation you had at the start, and then you're saying when you're working with this minimizing this norm on the transfer function, then that gives you another set of numbers to kind of define the sort of threshold. Like what
Yeah, the main
new message here?
okay, the new message is
Because I haven't just done a course on standard robust control theories. I don't know the reference point of your new ideas is. Do you know what I mean?
Okay, fine. That's the main point is that in LQR that we do not incorporate the external shocks to the system, or the disturbances measured, for example, sensors, all of them are ignored, okay? So, and in this case, the H infinity allows you to control for these disturbances generally, okay? And we'll show you that when the system is stable or not stable, okay? And that in terms of why we set that threshold that Nadav mentioned, actually that comes from the safetiness of the system that the system can tolerate, okay? That we can say, okay, this is the safetiness range. That then we set the conservative, for example, threshold. And then in terms of the comparison, I think that we should wait for this point as well. There is another measure that maybe answers some questions that I wanted to talk is a structured singular value or mu. So in terms of H infinity, the shocks are not structured, but you can have structured disturbances. And in that case, with the structure uncertainty, we can use the mu. Also, this measure also is used in the robust control alongside of the H infinity measure. That H infinity is a measure to shows the robustness of the system. So this is another measure. I didn't work on the mu to measure it, but it's also actually it is less conservative than the H infinity, because the delta is the structure disturbances that we have an idea about them. Okay, so is a matrix. The IM is the M is the matrix of the. This stands for the same of T. Yeah, T. Yeah, transformation. Actually, yeah, yeah. So here is. Yeah.
Maybe I think some confused about like you're talking about the feedback loop, the closed loop transfer function based on the open.
My talk is about closed loop, not open loop. Yeah.
Yeah, but the G right now is closed loop or open.
No, closed loop. Yeah, the closed loop.
So that means that the normal should be less than 1, right?
Yeah. So here is the comparison of these measures. You know the disk much.
So the closed loop is when you say, okay, I do have the strategy how I adapt my input, and that's adapting the transfer function, and then
Yeah.
this is kind of the new transfer function.
Yeah, the new transfer.
Yeah.
Kind of like you have a controller like.
Yeah. Okay.
Then have like a feedback loop.
Yeah.
Then you have a closed loop transfer
Yeah.
function.
Okay.
That's totally depends on how large the K.
Mhm.
Make it
Mhm.
always
Yeah.
stable.
Okay.
Yeah.
Okay.
Yeah,
So
yeah.
so
So talk about if the
Yeah.
open loop,
Mhm.
then HG norm,
Yeah.
the last norm, at the maximum norm, is still
Yeah.
at a certain number.
Yeah.
Then decide what the K you use. For
Yeah.
the
Okay, so basically, if in my open system, the infinity norm is over one, then
Yeah,
I know
yeah.
the
How-
open system is unstable. I have to design a controller,
Yeah,
and then I design that in order to have for the closed loop transfer function to push the highest eigenvalue.
Mm.
like the
one.
limit of the K you need.
Okay, yeah, okay, and then I know I can control it then with the assumptions I have.
Yeah, yeah.
Okay, thanks.
Okay, here is the comparison of different methods that we have. The disk margin that we talk is a combination of the G margin and the, actually that it's the gain and phase feedback. Okay, so and H infinity is for unstructured dynamics disturbances, and the mu synthesis is for the structure that I mentioned, but it's more complex to compute. I didn't work on this, but it is less conservative than the H infinity. The same topic that we discussed about the safeness and how the system can tolerate, how much the disturbance the system can tolerate to be stable. Yeah.
So more conservative systems, more robust.
Yeah.
I have some thoughts on this topic that I think would be good. I don't want to interrupt the flow, but if there's like a natural point to sort of extend the scope,
Mhm.
then I'll share those thoughts then. But maybe best not to wait until right at the end. About like conservative, basically,
Mhm.
whether how to be thinking about that in that brain stimulation.
Yeah, in terms of conservativity, we can compare which is more conservative. This margin is more conservative, and the H infinity is between, because the mu is less conservative than the H infinity in robust control. Okay, so in regular control that we use, this margin, they are the high conservative. Yeah. So, and here is a summary of this table that I explained. And this, so this one? No, I just, because we discussed, oh, you wanted to, okay, yeah, this is we should consider uncertainties because they are not evitable. Okay, so, and I mentioned this is a summary of the discussion. Okay.
Yeah.
So the classical margin, they are quick and intuitive. So this margin simultaneously considers the gain and phase, okay? And H infinity is developed to robust design, okay, for general. It means that unstructured disturbances, and the mu is for a structured way, the disturbances, okay? And actually, it is less conservative regard. This is the description of that table and the summary of what we discussed. But it is more complex to compute. Okay. So, and this is the system performance example. Yeah. Yeah, we talk about this, but here the normal is that we have the initial point is x, the system is 0, okay, the vector is 0, so, and the peak gain, suppose that approximately is equal to 1, okay, then as you see, the uncertainty increases, the peak gain rises, okay, monotonically, as you see. Oh,
Something.
yeah.
So the peak gain is the K, or
Yeah.
so the peak gain is determining how strong it is.
Mhm.
Is it like that?
Yeah, the peak gain, yeah. No. At the initial, when they have the system as a normal, the peak gain is 1, okay? In my example, it was 1.0.4%, okay? So it means that when the x is 0, the peak is computed 1, okay?
What is
At initial condition that we assumed here, by this assumption that x as initial x equal to 0, so the peak means that this is normal, that the system or it's converged to stable, it's totally stable, okay?
what's the definition?
Yeah, okay, yeah. See, you have a system, okay? You have the inputs and outputs, okay? So when the input is 0 and there is no disturbance to the system, then it should be 0. The output should be also 0, is it? So in the simple linear form, okay?
The gain one like a critical point.
Yeah.
It can go
Yeah.
into,
Yeah.
like,
Yeah.
how-
So this is just to show that what does the robust stability margin that we had. So for example, when when the peak gains go to infinity, okay, then x will be 2.3 times. This system become unstable. That's okay. Yeah. And when the system is totally unstable regarding the worst cases, here is 2.3 in this example. And here is that I explained this. Just let me see if. So, and this here, as I explained that 2 measures are used for the robust control, but there is a mix of H2, H infinity that some research use the combination of them to set the control system. And in those cases that we have the Markov jump, for example, mostly in the differential games, they use the mix H2 and H infinity control. So for example, when you have multiplayer, and even in the case of the neuroscience, you can assume that the nature or the body is a player, and also you as a physician that you treat and set the input, you are another player, and you can set a differential game. That is another topic that totally are one of the application of the robust control is the differential games, and they use it.
Sorry, briefly clarify again, what is the difference between H2 and H infinity?
I explained that what does H2, H stands for the regular, okay, but H infinity controls for the worst cases. Yeah. So regarding the topic that we are talking about, the neuroscience, I am not expert in this area. I just grabbed some idea of talking with you. I reviewed the literature. Is there any concern about the robust control in neuroscience or not? My question was that. I reviewed the literature and I figured out that some papers and some research have mentioned to the importance of considering these type of uncertainties and the room for the robust control. For example, for the DBS that you have worked, okay, in Parkinson's disease, actually they use these pulses, okay, to suppress the abnormal oscillations that have, and also you use the closed loop neurostimulation, okay, that adopts this input control, okay, on real time. These are the literature that's regarding the neuroscience that work on the control, okay? So, and here I mentioned that how and why these are important. I just briefly reviewed the literature. I don't know if you need, because you are expert in this. This is for me, not for you, to review this literature. but here I, for example, reviewed the background of the paper, the mechanism that they designed, what was the goal and the impact, and also I mentioned the difference. I don't want to take your time for this. Just let's go to this. This is actually I can say that's a system that I grabbed from the literature about the neuromuscular control. Okay, so as in any controls, you have a plan. This is your system, and here you have the feedback that you have your control, and here is the sensors that that provides the information for the actually for the control. So, and then the neuro commands will be sent to the muscle, and muscle will force, okay, and then the body movement. Again, you can measure the movements and by the sensors, and then again, and it is a real-time system, okay? So this is familiar to you. So, but the most important is 2 points that we can incorporate the environmental, okay, perturbations, and also the perturbation in the measurement. These are 2 points that at the beginning I mentioned that requires to think about the robust control because of these disturbances. If we do not consider this environmental and these measures, the error or the disturbances in measures, so that will be any type of the regular control, PID or full control or neural network control. This means that you have the mathematical system and you have here a controller. So then for the controller, you provide some input to the controller which measure the deviation of the performance, okay? And again, you have a closed loop control system. But that point is that we consider both disturbances, environmental, anything comes from the environment, and also the sensor disturbances that comes from. So here is the description of the system. The right-hand side was the plant, as I explained. You are familiar that is muscles that execute commands by generating forces and body movement. So as the consequence, so the actually the output is the body dynamics. So, and here is the control and the feedback that we have. The CPG is the central pattern generator that produces rhythmic patterns. So this is a type of the controls that is used in the literature. Okay, so I got this from the literature and I explained it. And for the sensor system, we have for example, the vision, the measures, and then the others. And this part is familiar to you. Okay, yeah.
So do you know what the reason is to use the CPG?
Oh, no, just I told you I'm new in this area. I just got this from the literature. There was a two papers I read from, yeah, I have the papers.
Do you know they justified by kind of a normative thing? So by the idea the brain should have that in order to
in the paper, yeah, explain, yeah.
Based on observation that they say, okay, we have some brain rhythms, and so we want to model them.
I'm not sure, but I got this from the paper. I will go to the paper in deep and see what is the reason that they use this. I have no idea, but I wanted just to see that, yeah, this is a system and the control, and our concern are those environmental, yeah. I have no idea. I'm not a neuroscientist. Yeah, I got from their paper the idea. So, and the functional flow of the here is that, for example, we have the environment, okay, that they create the perturbance or the disturbances, okay, they affecting the sensory system and body, both of them, okay. Then the sensory inputs are processed by the sensory system, and the controller here CPG plus reflexes generate the neural commands, okay, based on the information that they receive. And then the neural command activate the muscles, and the muscles force the body movement. And again, the movement affect the environment, and environment affect the body movement. So again, this loop is in real time repeated. Okay. So the key points is that the system function as a feedback control loops with continuous sensory. Okay, so that's I explained. And the reflexes that we talk enables the rapid and automatic responses. Okay, so and here I'm not sure about this, but as I understood that this is the CPG is like any control that produces the basic rhythmic motor, for example, to patterns that even if we have no input from the sensory, okay, that could be video. You can set it. I'm not familiar with this part, okay, that I got from this. And the most important is external disturbances that affects both the sensory inputs and the mechanical responses that comes from the body. I mean the body movement. Okay, so here our explanation. Yeah, again, I went in detail. That was summary. I don't want to go to these loops that how it happens, you know. So, okay, let's go to the robust control. So actually, the goal was to control for those external disturbances in the system that both affect the output, for example, the body movement here, and also the sensory measurements, okay? So here, the objective is to provide a unified and solid approach for the simulation control under uncertainties that have, okay? So we assume that the model brain simulator interaction as a stochastic differential gain. As I explained, that we can have the nature and also the controller, so there will be a gain between them. So this handles both randomness and worst case, as we explained, provides systematic method for controller system and bridge between neuroscience and control theory. And the outcome is the basic for the designing adaptive and robust and patient specific neuro stimulation strategies, because you know that in control system, one of the critical point is, and the basic point in the robust control is that the system are not similar. When you develop a mathematical model, for example, even for a drone, for example, you control the drone and the output is the drone velocity and is also the orientation. So any drone is different from that. You set the control for that, okay? So in any case, you need to adjust or to adopt a controller for that case, okay? So you cannot generalize. In the case of for example, Parkinson that you are working, maybe you cannot generalize that system to another. I don't know. To people, individuals differ personally. Yeah, the differences. So yeah, and you need to control for that. So this robust control allows you to have more robust system. Okay. So, and the general goal is to stabilize the neural activity, okay? But we know that what is the healthy equilibrium, and the others are around this healthy equilibrium. So we wanted to stabilize the neural activities around this equilibrium, okay? And okay, so and suppress the pathological patterns. So our challenges are the same that I mentioned: non-linearities, high dimensionality in a state space. These are challenges that we have and when we model generally. And we have unknown disturbances that we don't know, we have no idea about. They are not structured. And measurement noise and partial observability, maybe we have disturbances in the measurement noise, and the safety constraint that Nadav mentioned, that how we can set the threshold. These are different, and we should figure that why 1.8, why this threshold. Okay, so, but however, robust control guarantees against the worst case disturbance and systematically designed feedback stimulus protocol that are good for just in the cases that the patients are different. And actually, there is a trade-off between the robustness, and this can be used for the controlling to the trade-off between the control, the conservativity, and also the. So here is a simple model that I simulated. I assume that the dimension of the model is 2, so we have 2 state variable. Okay, so and also time is 10 seconds. It's not long time, and I break the time to 0, 0, 1, and initial state I assume that x1 and x2 vector are here, and I assume that we have the same disturbances. Okay, the system, okay, faces the same signals and the same stochastic norms, and the disturbances that realize, and we will compare these results. Okay, so this is the basic result that I got. I don't know if you can see the colors, blue and red, x1, x2. So these are the closed loop state trajectory. Okay, I solved the system and I simulated the closed loop. This is the base, and then this figure compares the nominal and robust control. So it shows the performance or trajectory of x1 and x2 under 2 regular and the robust controls. So, and the difference shows that the robust controls for the actually for the disturbance, external disturbances. So here this the blue one is the robust for x1, and as you see, sometimes it's low, and here is above. So the reason is that the system is sensitive to that threshold that we discussed. Okay, so here when the robust control underestimates the performance of the system or the trajectory, estimated trajectory, maybe is because above a level of the threshold that the performance of this norm or the robust control will be less than the regular control. It is not the case that always the robust control, okay, is better than the regular control. We should consider this point. Okay, so this shows that up to what point. So this is the result that I got, and my interpretation is the difference in, and it could be regarding the safetiness protocols that set the threshold and the others that maybe from a threshold, above that threshold, or maybe we can set, sorry? The system is 2-dimensional like this, that's I explained. The equation you mean that behind of that? It's in the MATLAB, I can show Dennis. Yeah, this is the description of the system that here, here is the 2-dimension system that I assume, like the initial the system that I showed you. That's LTI system. Yeah. So, and the robust control maintains stability despite disturbance in the noises, and nominal control show larger oscillation. If we consider the total oscillations, maybe we can figure that the oscillation will be higher. Yeah, we can compute it, the total variations when we use, but somehow the performance are not as the same, here they are the same, but the total oscillation is important as well to see.
Is this not just kind of relaxing to steady state from its initial condition? Is it stable?
Oh, yeah, that's another thing, this is just to show the performance under these controls, okay? So, yeah, the other is that to figure the stability of them. Yeah, I think that I calculated, but I didn't
Do
ring.
you know that this is the action of the controller that's doing this, or is it just the system relaxing to its steady state?
Here, my concern was to figure the oscillation and how is the performance in terms of the trajectory variable, for the state variables. Okay, but in terms of the stability, I can compute them. I think that I have already computed them. Sorry, I
Is
didn't.
this a closed loop control?
Yeah.
It's two different.
Yeah.
kind of control.
Yeah, two different type of the H infinity robust and normal. That I call the nominal LQR. So we have two types of. Yeah, that here it shows that the robust control is less oscillated than the performance of this trajectory shows that as you see that the blue one is more stable generally. The oscillation is less under the robust control.
I'm sorry, because I don't see it, because if I look at the difference around.
Yeah. You mean that generally this blue and this, you mean that this is the red one, okay? So here the difference is the gain, first of all, okay, from the robust control, that the performance of this is much less than that. So the other thing is that, yeah, I think that I calculated I should go to my.
My friend's like, if you drop the controller, then you're going to get this relaxation oscillation anyway. So how do you know what the contribution of the control input is to the convergence? What it's trying to do, is it trying to converge to zero?
Yeah.
Right, but it's also relaxing
Mhm.
from its initial condition.
Yeah.
That's what you would do anyway, whether it's a controller or not, depending on what you chose the initial conditions.
Yeah, that is I set this the driving metrics for the state system that was hypothetical, and I use different, but to have a more realistic system, we can have, for example, we can compare the trajectories under two control system with the actual data as well, if we have observation, the real observation.
You just need a third curve, which is like.
Yeah, if we no control, yeah, I can make it. Yeah, that's a good idea. Thank you for this point.
If you to a small computer, that's my high gain.
Yeah.
High gain, that performance, especially because you only consider the statement at zero. So the performance, especially the overshooting, will be higher. Higher than the regular one.
Yeah.
Yeah, right. If you show in the end, maybe the red one, falling to zero faster than. No, the other way, the blue one.
The blue one, the blue faster. Yeah. Yeah, that goes faster. Yeah. Yeah, that is. Yeah. That is. Yeah.
Yeah, you have to consider performance.
Yeah, the performance. Yeah.
Right now.
Yeah. In this, yeah. Okay, so thank you for attention, and there are some resources that I reported in this presentation. Thank you. Question? Sorry, actually, in terms of question, I know that there are too many questions from the technical point, the neuroscience, and I in the neuroscience, absolutely, I'm new. I just, but yeah, I am happy that I got good feedbacks from you regarding the designing of the system. Okay, right. That was a pleasure.
But right now we have a mathematical model for the whole we have a depends how many population you have. Each population will probably have 3 population. So like fix the differential equation. The measurement like if you're using the model to design a controller, maybe there's some stimulus on the certain region. You can push those the EEG like power spectrum, for the reference. Maybe can you do based on the model we have? Can you design those the controller?
Yeah, let me involve it. Yeah, we can talk it later. And
Yeah, especially when they have model parameter, right? But
Yeah.
you have a model parameter should be adaptive to the person, this personal brain, based on the EEG. Then you can based on the state from your model to design the stimulate. If you can do that one, maybe good. Yeah.
Let's talk in later. Okay, yeah, we will talk more. Okay, thank you.
Like 2 thoughts based on your talk that might be interesting to explore connections with neuroscience or cognitive science. One, I was wondering if it would be, or maybe people are using robust control in more clinical settings where you need like guarantees that some I don't know measure won't I don't know, some life critical measure should go beyond some level.
In terms of neuroscience, I mentioned to the literature that I reviewed here just briefly, but yeah, the robust control is used in industry, and that's
So this was one of the things I wanted to comment on actually. It's
Yeah.
like I think it's worth kind of bearing in mind. I think robust control and the space you're in here with the sort of worst case scenario, clearly like the inspiration is like industrial process situations, or I don't know, airplanes or something where like it would be absolutely, catastrophic if certain things went wrong,
Yeah.
right? So you like really, really want to think about the
Yeah.
worst case scenario and sort of bias your design to like making sure that nothing goes wrong, right? And like employ the sort of tools of the control theory framework with that in mind. I think the neuroscience situation is on the other end of the spectrum, because basically the situation you're working in, which is unlikely to change anytime soon, is if you're talking about brain stimulation, for example, which is the most clear analogy here, like all the safety parameters for the devices that we use, those are kind of they're not up for debate, right? They're kind of defined on non-control theory based criteria, right? They follow like long procedures of guidelines on like what is considered safe, right? Those set the limits on what you can do, and there's no role for like the control theory in thinking about like the limits of the worst case scenario. Like the limit on the worst case scenario is the limit on the on your parameters of your device, right? And those are defined, those are chosen such that like you cannot make it do something dangerous.
Yeah.
So actually the thing that I think that the problem space that's more relevant in this area of brain simulation is the other end of the spectrum, where like the problem is that we have weak effects or no effects, and our goal, I think, is to sort of make use of some smart methods to kind of find out how we can have strong effects with weak perturbations, not make sure that our perturbations don't induce strong effects, because to some extent, like it's not our job to do that. The job for that is like officially it is the safety part of like like stimulation design device. We don't have control over that. If we were manufacturing new devices, right, and we were involved in that sort of like safety, but maybe, but even then, like, they don't use control theory for that. I think that there's other things that are involved in them. So we have to figure out how we can have big effects with small perturbations, not how our small perturbations can be designed to make sure they don't have big effects. That's not the problem that we have.
Okay. So I remember regarding your comment, for the first time in the mathematical oncology, I was talking about this robust control in mathematical oncology, and I got a response that was that the guy said, in treatment, in cancer treatment, there is no uncertainty. And when someone is diagnosed with the cancer, they should follow the robust, strong, rigorous protocols, and they cannot, for example, deviate from that. Everything is designed and it's out of the control. So it means that there are some protocols that the physicians follow these protocols robustly, okay, solid. And I say, okay, fine. In the literature shows that 28% of the patients in North Africa, they do not follow the treatment. And in UK, for a hormone therapy, they observed for 11 years the patient's adherence to the hormone therapy, and they figured that the difference between the progress is significant when the patients are less adherent. So I have no idea about the neuroscience because I'm absolutely new in this area, maybe, but literature, I reviewed the literature. There are some comments, the papers that I got, that they mentioned how it's important to incorporate these uncertainties. And if you give me more time, I will go more in detail why and justify that regarding your comment that it is out of this scope. But I think that there are uncertainties, and you can, maybe your simulation perform well, but it does not follow the reality. So the model is not the reality. We should minimize this deviation from the reality and the models. Maybe the model by itself is good and performs well. But my main concern is other disturbances in the nature of the patients, anything that we can mention. However, that was we discussed with Yupeng about his study, and he said that maybe some movement from the patient affects the results. And we were thinking about it. Maybe they are minor effect and ignorable, but yeah.
I think the uncertainty question is right. You know, that's it. Like, there's system uncertainty, measurement uncertainty, variability, right? But again, like I think the objective in terms of incorporating that should be to try and make sure that that doesn't make your effect go to zero, rather than the uncertainty leads to a danger of your effect going to infinity.
Yeah, there is a balance. Optimization is that you should balance between, this is the trade-off. Yeah, I mentioned in my slides as well. Yeah, that's great. Yeah.
Yeah, I know that the clinical protocol can be very conservative because from my previous experience, people kind of use 100 filters for the DDS for the analysis. Then everyone follows that 100 filters, and nobody knows why, but they just follow. So, so it's like when people are designing the clinical protocols, they are very conservative. They kind of converge to a very small range, and they don't allow themselves to fluctuate around that. So I think maybe this is part of the value of doing computational modeling and control system to try to explore the wider range of parameter space and to see, even in the simulation, to see if it can generally simulate some therapeutic effects. And then the next step could be try to further validate those explorations in experiments, for example, with animal experiments first, or some simple trials for the clinical case. Yeah, for me, this control system together with computational model, it kind of opens up a new range of parameters that could be potentially more beneficial than existing very conservative protocols.
Good, thank you.
One question on the uncertainty also with regarding the context, what's the difference between control theory of engineering and now if we apply the neuroscience? Because I would assume that if I try to control a plane, I know the system quite well. I mean, there's some uncertainty, but I think my model of the system is quite accurate because I kind of constructed the plane. So I know that very well. And so it's also kind of easy to model. I mean, I do have uncertainty everywhere, but I can do that very well because I know the underlying mechanics quite well. I would not say that in neuroscience that's not the case. So our models aren't that well.
Yeah.
So doesn't my dad also change the? My dad also posed a challenge to transfer the insights from control theory to neuroscience. That they very often have the implicit assumptions below the underlying mechanics to a certain extent, and we don't really have that certain extent in neuroscience.
Yeah.
Oh, that's great that you mentioned about the uncertainties. Actually, in the plane that you mentioned, you mean that those uncertainties in the intermediate environment, I mean, you mean that they are clear to you, but I don't know if I got you properly. You mean that, but that's not the case. It means that in terms of figuring out those uncertainties.
No, so on the plane, there are uncertainties in the environment. There are also uncertainties on the sensors, and there might be also slight uncertainties in kind of the action.
Yeah.
But the underlying system, how I constructed the plane, which wires go from where to where, which controls I have. Yeah. So the underlying system, I know it quite well because I designed the system.
Yeah.
While in the brain, the whole problem of neuroscience is kind of we don't really know the underlying systems. I mean, we do models which are but if we compare the underlying system to our models, we don't really know anything.
You mean that there is no room for the closed loop? You mean that there is no room for closed loop control system? So you have just a stimulus to the system and the output, and you say, okay, it is in the protocol. That's it. No closed loop. Because you have no reference system. You mean that you have no reference system even to have the to use the control theory generally. I mean that. So there is no room for the control.
We have substantial system uncertainty.
Yeah.
Of course, they have a room for control system for sure. Because the model, even we can use like a deep learning model to learn how the people's brain react those response. Once we have like a mature, the machine learning model, we can using the feedback.
There's also means that we don't have not sufficient understanding of the underlying mechanism.
Yeah. I got it. But I'm thinking that. So I always think about this. We have a toolbox. The toolbox is, for example, ODE, PDE. These are the toolbox that the mathematician have in their hand and can apply and say, okay, my concern is to predict what will happen in pandemic, regardless of what is the intervention by the government. So in that case, it's okay. The mechanism is or could be described in this system, differential or dynamical system. So, and if the model can predict, okay, there is no need to go further to add any other assumption. So if you mean that, okay, we can set this dynamical system to explain the dynamics of the system, and if we have any intervention, we can incorporate as a parameter or incorporate as an equation into the system, then so there is no need to go further for uncertainties. Maybe that's true, but I'm not 100% sure. Always there is a room to consider uncertainties. This is my concern. Otherwise, I have worked for 6 years on the mathematical, the deterministic, the ODE system in epidemiology. I understand why those models are not capable to incorporate these uncertainties that comes from the behavior of the people. And I'm sure that in neuroscience also there should be some, even the hormones, I don't know, the body, and maybe different people with different parameters are not the same, and we cannot have the same protocol for all of them.
The stochasticity in the
Yeah, yeah, yeah,
Stochasticity.
yeah. Stochasticity is the reality. You cannot ignore stochasticity.
But problem is not only stochasticity, but really this, I mean, this system's way more complex. So
Yeah, absolutely. It makes more complex.
all the complex.
Yeah, that's the
I
very.
mean, we have some rough idea what's going on there, but we are
Yeah.
very
Yeah.
far from the detailed models.
Yeah.
which is
But
fact.
the requirement for considering this scarcity came from the literature that I reviewed, at least these papers that I just read quickly, not in detail. But if I have time, I will go through the details. Yeah.
Definitely, the mix. H2 controller, that
Mhm.
means some frequency maybe go unstable.
Mm.
That's the something the brain has. Brain the dynamic, usually people talk about this closer to the critical point.
Mm.
So if the noise can go to the deeper range.
Mhm.
So rather than for the stable, they do the like a left component like close to zero. In that sense, the brain, right? Yeah. But the other hand, I think the high level like thalamus, the like deep the subcortical, they may be like more conservative to assign those the cortical what kind of job that you should finish. That in that case, maybe it's HMN. Just
Yeah.
So I kind of like the mixed idea is good.
Is it a bit like the idea of doing an elastic net, kind of having like different
different
configurations?
Yeah.
And just weighting them and saying,
Yeah.
okay,
I think
I
those
try to find a balance.
yeah.
Because I don't want to have to like two of these cases, but I also don't want to carry what worst case, but the one trying to compromise.
Yeah, they complement each other. Yeah. Keep the stay alert, for the brain, like the need, the critical point, but there's some part of the brain that I will make sure everything now moving on.
I saw that the control trajectory for the H2 and the H infinity actually has a lot of overlap. It's like they both decrease or they both increase. So is it because there is a kind of overlap in terms of the mechanism or the equations?
No. That was the comparison between regular and robust control, not H2. And that was a regular LQR, okay, and under the H infinity or robust
What is
control.
the reason that they consider
Maybe the point that John mentioned, that this disturbances that I consider are not significantly or amplified, that it maybe because I can change those disturbance assumptions, and that will be completely different behavior. Yeah. Yeah. Initial conditions, anything can, yeah. Yeah. Yeah, there are no so strong interactions, and yeah, we have different, reason for that. Yeah, but in more high dimension system, maybe, yeah, it will be different. Yeah.
So here are three kinds of closed loop type scenarios, the neuroscience scenarios, the brain stimulation scenarios. All of which we're sort of working on and are of interest. And there are sort of concrete questions that could be addressed. There's a lot more to say than this. I'm sorry about the handout.
John, do you need to use this one? To be recorded for the others that are not here.
Sure. Yeah, okay.
Thank you.
Hello, everyone. But it's just, I'm just kind of brainstorming for people anyway. So like, I think the theory is awesome, and then the difficult part is like translating to the concrete scenarios that we're working with. So to just articulate some of those, we already talked, and Yupeng is the expert in the room on the DBS Parkinson's case, right? And the characteristics of this, broadly speaking, is you want to suppress a 20 hertz oscillation using 130 hertz frequency stimulus in real time. So yeah, 20 hertz. I mean, that's like the oscillation you want to suppress, the intrinsic oscillation. You I guess want your controller to be working in real time, updating in real time, or something in milliseconds, and you want to suppress I guess system instability, or this 20 hertz frequency. Is that like a reasonable summary?
Yeah, it's like the beta band.
Yeah. Yeah, and that's what the tremor is in Parkinson's. So it's quite kind of easy to get your head around what that basically corresponds to. Okay, so that's one major closed loop neuroscience stimulation context. Another, here are two others which are a little bit less, well, yeah, I guess a little bit less canonical than this in terms of how they fit into like the framework of control theory, essentially. So one is doing TMS with what we call an alpha phase triggered algorithm, which I'll explain. Sorry. Oh, repetitive transcranial magnetic stimulation. Okay, so this is, as opposed to DBS, where you have an implanted electrode that basically has maybe a diameter of like 2 millimeters or something. What's the size of the? Yeah, so it's like a tiny, pin that's going in the brain, and then it stimulates, and it has a field size of about that. Okay, that's DBS, right? TMS is, I've got a magnet, I've got a coil that's like maybe the size of my hand that you're running a current through, and you put that on the scalp, and then the magnetic field penetrates the head. So this is now kind of centimeter scale magnetic field that's penetrating the brain. So it's less focal, and you're targeting different brain areas. But
In terms of the concentration, specific region, which is
it's basically a largish part of whatever brain. Okay, the motor cortex and the frontal lobe are usually where we think about. It will be a few centimeters of tissue that's stimulated, and then maybe a smaller amount that's stimulated strongly because the field strength drops off from the distance. But these are two different scenarios that differ in terms of like the time scale and the kind of mechanism of interest. both TMS. So the third one is the one that Yupeng's working on with us, which is the plasticity model. This one is what my colleague Christoph Zrenner is basically a world expert in, which is we call alpha phase triggered TMS. So this is not closed loop, this is open loop. But I think it has like the potential to be closed. The question is sort of how, but the characteristics of it is you have this intrinsic 10 hertz rhythm in most of the brain, which is sort of quasi-periodic. And the idea is to do like a real-time estimation of the phase of any given part of the brain that you're stimulating, because they're slightly, think about it this way, like every part of the cortex is roughly, it's usually oscillating at 10 hertz, but they're not all in phase, right? But their natural rhythm is 10 hertz. So you choose the part of your brain that you want to stimulate. estimate its phase in real time, and then the aim is to basically, like, from your real time estimation of the alpha phase, time the stimulation pulse either at the peak or the trough of the algorithm. Okay, so this is a little bit like if you just had a kind of fixed 10 hertz stimulation, but it's adaptive in time from a real-time estimation of the current system state, the system being the phase, the instantaneous phase of the algorithm. Okay, so this is, and the way that this then works in practice, like in the lab, is basically like measure the phase in real time with the EEG, have the TMS kind of connected through a box that does some real-time processing so that it's fast, estimates the phase, and then triggers a pulse. And the pulse is then timed to occur at the peak or the trough. Right. So this is a roughly 10 hertz. It's quasi-periodic, kind of like rough, it's not a fixed, it's not as periodic as the 20 hertz, I don't think. It's real time, but it's a little bit slower than 20 hertz. Right, it's 10 hertz, but still, like, you need sort of millisecond level precision for the phase estimation. And your goal is different, right? So in this case, like, the aim is not to suppress this rhythm. The aim is to enhance this rhythm. The way this rhythm is enhanced is sort of unknown, right? We don't know, essentially, like, we don't know what happens when we do this. We just think that when we do this, and empirically it is the case that when you do this, and then you do this repetitively, then it will enhance the amplitude of this rhythm on a when you stop stimulating and then just measure it endogenously. Okay, so goal is not to suppress. Goal is just to, like, identify the phase and then time the stimulation to match the phase. And then there's sort of a black box, like, loose concept that is having an effect on the structure of the system that is generating the oscillation in a way that we think is good. Now, I guess sometimes we might not want to enhance. Sometimes we might want to suppress.
Can we say they stabilize frequencies? The domain of
I would say the situation at this point is, like, we have very little idea what it is we even want to do, and how we can do it, right? So it's like, I have to say that, discussion section of paper, we're like, more work to be done. Oh yeah, but what I mean by enhance suppress here is that let's try saying this. So I mean, to enhance or suppress. Yeah, basically, like, some work is focused on enhancing, some work is focused on suppressing. We're not sure which one we want to do. Okay, there you go. So the third scenario is related to this, but it has a kind of slow component in it. So this is, if you like, a very phenomenological model or phenomenological concept to the system, which is like the system is just the phase. It's something that is producing a phase. There isn't even really like a model of the system. But if you were to do closed loop on this, you would probably define some simple, like, phase oscillator and kind of frame it that way. This third scenario, there's also TMS. It's also essentially the same type of stimulation protocol, but not phase triggered. So the things that are different here are now, like, the type of stimulation and the aspect of the system that we're trying to access, right? So this case, the frequency, the stimulation protocol is called intermittent theta burst stimulation, which is basically like multi-frequency stimulation, and it's also acting on a multi-frequency brain system. So it's multi-frequency in the stimulation because with intermittent theta burst, you have a 40 hertz bursts that are nested on a 5 Hertz carrier wave that is pulsed in 2-second on periods and 8-second off periods for a duration of 5 minutes. Okay, and then sometimes you repeat that every hour. So there's a lot of frequencies in there, and like which one's most important is hard to, yeah, it's probably the theta, but it's multi-frequency. And then the other part of the multi-frequency is like the model that we're working with, which is the actual idea of how that plasticity effect manifests, which is so this is something that's not very well known. We're sort of pushing the frontiers, or like picking up some of the more advanced work in the field in terms of how we think the underlying neurophysiology of the plasticity effects occur. And the kind of key properties of that is there are essentially sort of intracellular processes that operate on tens of milliseconds. Okay, so they're slow, they're sort of infra slow, like maybe 0.01 to 0.1 Hertz. And this is something, things like an intracellular calcium concentration that fluctuates, but it also, in the models we have, has this sort of called homeostatic feedback that also influences its kind of temporal properties. And the goal here is there's kind of maybe two goals again: enhance or suppress. But the idea is that basically certain frequencies will result in ultimately what we call long-term potentiation, which is the synaptic weights in the system get upregulated or they get downregulated. So broadly speaking, like what the nominal objective of therapeutic TMS is to induce long-term potentiation. So it's to enhance, but the thing you want to enhance is the synaptic weights, okay, which isn't necessarily, it's not like a dynamical property, it's a structural property. However, there is also a dynamical property, which is actually the 10 Hertz rhythm again, that we think you actually want to suppress the 10 Hertz rhythm. But this is a separate line of thinking too, that we want to enhance the synaptic weights. And one of the open questions is like, what's the relationship between these two? And they might be sort of consistent in that, like, it might be the case that enhancing the synaptic weights, when it's done the right way, suppresses the 10 Hertz rhythm, and so we kind of those two fit together. But it's a bit unclear. Okay. Now the closed loop part of this is also very much up for grabs. What we're working on with Yupeng is like keep it entirely within the model. So don't really worry too much yet about interacting with the brain data, which is actually fairly well understood and figured out for these two from a hardware and a recording level. So these two are sort of implemented closed loop systems like that are there in the lab that we can use. We can do real-time stuff if we have an idea of what it is we want to do. This one, it's not so much that we can't do it. It's that we're not sure what it is we want to track, and it's just new, and it's also it's more theoretical at this point in terms of the model. So what we're thinking about is kind of, if you had full access to all of these state variables of the model, then what would be your kind of control policy for achieving some of these plasticity outcomes? And then we move to the question of, well, if we do that experimentally and we have access to certain observables which are kind of noisier and less direct than the system state variables, then, you know, how would we achieve the same thing? And then the final thing about this is that it's slow, right? So the plasticity process is slow, and I think the way to think about the closed loop element of the system would be updates on tens of seconds rather than potentially like millisecond level in this case. So these are like three concrete. I mean, I guess there's a lot of fuzziness from the way I just described this, but these exist. These are scientific problems that, you know, we're actively working on. lots of people are actively working on, and there's a good amount of like momentum behind like how to do it, and also why, what it would be useful for when we're going to figure it out. So I guess, yeah, that's sort of, I don't know if this is a useful sketch, but I would suggest, like, if we want to kind of progress some of the control theory discussions, we try and sort of focus on like what is a subset of these these use cases that accommodate some of the tools that we're interested in developing, and then we kind of win-win scenario, right? Then we kind of the application is clear and the problem is clear, and we've got some kind of concrete questions. My preference is for these two, because this is what I work on. Yupeng is, as I said, sort of expert on this. So, and to some extent, this is the most developed from a control theory point of view. But yeah, like I'm kind of more interested in these than these. But any work on any of these, I think, if we, in the broad scope of like, if we think this is the focus group the next few months, I would say, like, let's kind of have everything being picking off one of the subsets of this broad problem space. Does that sound like a good idea? Just a thought. What this doesn't have is any of the, I mean, we can talk about other scenarios. Like, so this doesn't have any of those things about like environment, body, controller, okay, which maybe you know, Nadav is kind of interested in some of that a little bit more. So this isn't like, we could add more to the list, you know. So when you think about that sort of organism level closed loop scenario, where you have like the sensory inputs, brain system, you know, central pattern generator, muscles, actuator, right? Like movement, sensory input, right? That level of like closed loop motor control, that's not this, right? So this is not really describing that scenario. If you were to go there, I kind of have ideas, but I guess that's sort of not my wheelhouse. So I couldn't sort of give any expert advice on that. But ultimately, like, it would probably be some kind of motor coordination scenario that you'd want to be dealing with and potentially that works with DBS. I mean, with DBS, like, you know, they're ambulatory, so you do have potentially like the muscle and the movement and the environment, I guess, in a sort of active system. But these two, this is like in the lab, stimulating the brain. There's no sort of cognition here. Basically, this is like, we do something to the brain, to some neurons. We want to measure what the neurons do, and we want to sort of get the maximum impact on the brain in that particular closed loop circuit. The environment and the sort of the brain in action, so to speak, is pretty much out of the picture. Thoughts?
To work, but just let me digest. I should go.
Yeah. I'm not saying this is a sufficient explanation to, you know, run away and work on stuff. Yeah, totally.
John. I have like two thoughts, but they're like here and here.
Right. Okay.
Or maybe, so the first question I had is particular on the DBS case. So if you use a 130 hertz stimulus to modify 20 hertz, the modified 20 hertz behavior, then I would assume you need non-linear behavior system to have that interaction. Or so the first question is, do you need that? And then the second question is, does it, because I thought control theory is usually operating on linearized systems. So do you need more flexibilities of control theory then to
I'm redirecting this question over to you, Peng. Hey, I think,
So, I think there are kind of two kinds of control system for the DBS that has been established. One is based on the controlling the or suppress the beta band frequency that is observed by the filter in the subdynamic nuclide. And that is kind of based on the observation of those beta band activity from the natural recording. And then there's a real-time system to turn on and off the DBS to suppress that beta band frequency. So yeah, that is what is kind of in practice.
Is it done with linear control theory or with non-linear?
I think it's just a very simple control system, on and off system. Right? When the beta band is above a threshold, then you turn on the DBS. But if it falls below the threshold, you turn off the DBS.
yeah, it's probably not, it's not even control theory. It's just like a switch,
Yeah,
like a
yeah.
threshold
Good,
switch.
it's so kind of really good way to-
That is something that has been practiced.
Yeah.
But in terms of the control theory, I know that people are developing more like theoretical models to kind of predict the big bang frequency. And that is more like hasn't been very extensively implemented. So I think people are trying to kind of such kind of system.
But definitely extensively published. And this is the thing, like these aren't new ideas. There's like thousands of papers on these things, but in practice in the clinic, it's not used.
Yeah, and there is another kind of control system with DBS, which is mostly for tremor signals. For example, for the central tremor, there is a measurement of the EMG signal of the tremor activities. And it kind of in practice it follows the same logic. It's like if the muscle activity or the EMG power is above the threshold, then you turn on the DBS. But if it falls below the threshold, then you turn off the DBS. So yeah, this is what in clinics. But there are also been ideas of exploring what is the underlying mechanism of what is happening. That is like the propagation from from DBS in the thalamus to the muscle activity.
Yeah.
Actually, this is my previous work on this to develop a physiological model to try to predict the muscle activity from the input gas. But this is also some ideas, and it hasn't been really invented, but it's kind of promising the future direction to implement that. It's fine. But what I want to say is that in clinics, the currently clinically implementable closed loop system is still kind of naive from my perspective. It's like on and off switch, but not a very accurate control. But this is certainly a field that could be further developed.
And so for the more sophisticated closed loop system, you wouldn't need to take the non-linearities into account.
That is kind of develop some sufficient or effective computational models to try to predict the biomarker. And then you kind of utilize this computational model in the control system. That is trying to figure out this idea of all of this.
I would say, like, reiterate previous point, like in the TMS context, I mean, yes, the therapeutic context is patients with depression come into the clinic, have this brain stimulation several times a week, and in like 30 to 60% of cases, they experience remission of their depression after 3 months, right? When I think the more sort of tractable problem space at the moment is actually, it's not that. It's the fact that the thing that we do for the therapy, the thing that we know about it, which the clinical effect is not, a little bit less so in DBS, it's kind of clear, right? It's like they've got a tremor, right? In depression, it's not clear because the effect of your intervention is 3 months later, basically, by definition. Although ultimately, like, the physiological effect is going to be fairly immediate, but we just, so the clinical outcome and those observables are like, they're not really part of the control question. The control question is more on these physiological proxies that we can measure immediately, and those we can kind of measure in healthy subjects. Unlike DBS, we can do these kind of something similar to what the therapeutic stimulation looks like in non-patients in a kind of restricted context, and see what effect that has on sort of normal brains. So we can kind of pilot and explore things a little bit more, but we have a little bit less sort of close measurement effectively. But the thing that the sort of modest, I think, objective at the end of the day is like, in that scenario of, let's say, doing these kind of protocols in healthy controls in the lab, like this study that we've just run for the last 2.5 years, and lots of other work that's similar. Basically, the intended effect, which would be this sort of plasticity inducing, LTP inducing effect that we measure with the kind of amplitude of a stimulus response, you see that in like 50% of people, right? So it's very variable. And then some people show like the opposite, they show an inhibitory effect, right? So even if we can just sort of move the kind of statistics of how often we see this like proxy physiological effect in healthy controls in a sort of restricted human neurophysiology experimental context to like the 90%, you know, kind of territory, from the like 40-50% territory, that'll be like significant progress in what ultimately becomes a translational therapy for brain stimulation. But it's not the clinical outcome. It's really like the effect of the stimulation in the first place. And that's why I was saying before, like, our problem isn't this scenario of like chaotic, catastrophic, extreme events. The problem is just a relatively ineffective response rate at that in the first place. So what can we do with understanding the system and some smarter approaches to things to increase the effectiveness, the like baseline effectiveness? That's the task as I see it.
On that case, I would assume that if I, for example, stimulate different patients with 10 hertz, that they would respond differently directly to this stimulation. So if I measure kind of I'm sorry, measure the direct reaction, direct reaction to that, or even if I had like a control loop, then that I would need like different parameters for that. So that this stimulation, so either the response to the stimulation or the response will be always different, and if it will control it, then I would, I would change my simulation a bit. Have there been studies examining kind of the different response to the stimulation, to the outcome 3 months later?
Say again.
So have there been studies looking at, for example, so because I can say that at the time of stimulation, it's kind of a control problem. So I am but I have a different readout. So I just have so I can just look at the EEG signal, for example, and I can simulate, and then I can look at the EEG signal, and I might use that to control. And from that, I could infer some properties of what went on during the simulation.
Yeah.
And have studies comparing that to the outcome of 3 months?
Yes, and there is like a weak positive correlation. Okay, so like it is the case both like empirically, but not sort of drop down. It's not like hugely consistent or strong, but broadly speaking, like, yes, it's the case that if you have a stronger plasticity effect, the local effect or the kind of short-term effect, then the clinical outcomes will be better. But that's not. So the reason why we think there's a relationship between those two, and that's the right way to think about this, is essentially because there is a weak relationship, and two, like, that's just how we understand what it does. So it's just like the best we've got, right? It's just like a working assumption, and just a general again, like working assumption, or if you like understanding of expectation that we're sort of missing the target a lot of the time, like metaphorically speaking, like we're kind of throwing darts, right? And so the general thinking around like what's going on with this like 50% response rate, or not even the 50% response. I'm not talking about the clinical response. I'm talking about the local plasticity response, right? Like that. The general thinking is well, we're so throwing the darts, we're just missing the board, right? It's not like it's so we just need to kind of get the darts on the board a bit more often, right? And then that'll be a good start. And we're missing the board in terms of like, and there could be lots of things going on. There's lots of work on the spatial aspect of it, which we're not really thinking about here, but then there's the temporal aspect of it, which we are thinking about more here. So maybe we're kind of figuratively speaking, like the way that we're interacting with this endogenous oscillation. I mean, this is a good clear example of it, right? It's like the idea of doing the phase triggering is that like we're just throwing darts at this, as in like a regular periodic stimulation set of darts, then we're gonna like miss the sweet spot a lot of the time. So like adaptively time to hit the, so those are like, we're just sort of missing a lot if we're not adjusting in that way. So that's sort of, I think, carries through to here, to this case, but there's a little bit more of a complex interaction when we incorporate the plasticity system, because there's sort of things like feedback processes that make certain effects kind of cancel out and go in the other direction if they're sustained. So there's a lot of like non-monotonicity. But again, we just want to like have a stronger effect at the end of the day. That's the objective. Shall we wrap up? Yeah. Yeah.
Just talking about the so the different control problem of the brain going the body in the world, in the environment. So we've been thinking about that a bit, and one argument we always use is that it has to be predictive control for different reasons. So it's going along with predictive coding ideas and so on. So because that would be more efficient. So that would mean that so that would mean we also need like controls of predictive theories of predictive control.
Yeah,
right?
well,
So
and that could be on the list. I mean, that's like tractable.
Yeah.
Right? Yeah, like a controller on an HGF, for example. Has anyone done that? Yeah, probably have. Should we give Mortaza a round of applause?
Is this a good time for people in general? If we want to, like, we can give this seminar series maybe 1 or 2 weeks.
Yes, we sort of have a slot of 2 p.m. for that meeting that we haven't been using. So either now or at 2 p.m. essentially, I would be fine with sort of co-opting our meeting slot, but it's discussion.
also just
Yeah.
On Wednesday, the new semester, I have a teaching, I think, and I should check my schedule. For
Why don't you
teaching.
poll on the slide?
Yeah.
and see what you think. Yeah.
Yeah,
Morning or afternoon or Wednesday, the meeting in general.
okay, let's see when is more.
I think, but if we do morning, I'd rather do first. I think. Be my preference. But like maybe just post a couple of times. See.
Okay.
That's
Okay, and how about Fridays? Everyone,
Fridays I'm usually
because I got your message and I will send it.
but we can do it.
Okay.
Kind of,
Yeah,
I don't
yeah.
mean we can sort of adjust the topics according to who's present, right? And then doesn't need to be everyone there every time.